Okay, talking about the pigeonhole principle today, and pigeonhole principle is a way to prove things, a technique for thinking, a way to prove things that comes up an awful lot in discrete math. Okay, so here's the basic idea: is that if you have a non-empty and finite collection of numbers, so a bag of numbers is a collection in which order does not matter and repeats are allowed, then the maximum value is greater than or equal to the average value. The maximum is greater than or equal to the average. I mean, it's perfectly commonsensical. So, and the maximum equals the average only when all the numbers are the same. So the idea is you'll look at all the numbers b0 through bn minus 1 and you compare the average. So you take the average, a, then you're looking at the sum of all the bi's divided by how many there are, and you do the cancellation and you end up with c. Because c is the maximum, the sum is equal to nc only if each bi equals c. Okay, so it's commonsensical and it's perfectly straightforward. If there are more pigeons than there are holes, this is the sort of translation of the pigeonhole principle into the word pigeon. If there are more pigeons than there are holes, then some hole gets more than one pigeon. So here there's 9 pigeons and 9 holes, so you get 1 and 1. But if there were 10 pigeons, some hole would have to get at least 2 pigeons. The average number of pigeons per hole is greater than 1. I mean, if there's more pigeons than there are holes, then the average number of pigeons per hole is greater than 1. So the maximum, which has to be an integer, has to be at least 2. Okay, so we're going to do a couple of examples of the pigeonhole principle, maybe somewhat silly examples, but we'll get to not silly examples pretty soon. If you pick 13 people, there are at least 2 who are born in the same month. Again, perfectly commonsensical. So here, the idea is that the pigeonholes are the month, and the 13 people are the pigeons, and we're putting them, each person gets put in a hole that's labeled with their birth month. If you're born in July, you could go in the hole that's labeled July. So some month gets 2 people. That's the pigeonhole principle. Of course, it could happen that some month gets 4 people. It could be that 4 people are born in July, and some month gets none. But the point is that the conclusion of the pigeonhole principle is that at least one month gets at least 2 people. Okay, here's another example, again perhaps a silly example, but it illustrates something like the idea. It's a question of coming up with the right meaning for pigeons and holes. So suppose you get dressed in the dark, you have 2 socks that are black and socks that are blue, but you can't feel the difference. So how many socks must you choose to be sure that you got out of the bedroom carrying a matching pair? And so the answer here is that there are 2 categories, there are 2 holes, black and blue. The pigeons are the socks, and they go into the hole labeled with their color. So how many socks until the pigeonhole principle guarantees that a hole has at least 2 socks? Well, 3. You don't know whether you'll have 2 blacks or 2 blues, but you have 2 of something. All right, here's another example. You often hear this example. In New York City, there are at least 2 people with the same number of hairs on their head. So a person has about 100,000 hairs on their head. So the holes in the pigeonhole principle, the holes, the categories, are just boxes labeled from 0 to 100,000. And the pigeons are the people. New York City has about 20 million people. That's way more than 100,000. So put each in the hole label with the number of their hairs, and so some hole gets at least 2 people. All right, or maybe a less silly example, a lemma. If you give me a set of n natural numbers with n greater than or equal to 2, then for any number less than n, 2 of the numbers in the set have a difference that's divisible by k. So you're giving me a set of n natural numbers. You might give me, for example, a set of 7 natural numbers, as in the next example. You give me a set of natural numbers, and if you tell me a k less than however many natural numbers you got, then 2 of the numbers in the set have to have a difference that's divisible by k. So here I took n to be 7, and I took k to be 6. So there are 7 natural numbers here. It has to be the case that at least 2 of these numbers have a difference, a minus b, difference that's divisible by 6. So a person would go through and say, well, let's see, 12 minus 3 is 9, so that's not divisible by 6. And 3 minus 9 is negative 6. Okay, negative 6, so that's divisible by 6. So maybe we'll adjust one of these and bump the 3 up to a 4. It doesn't matter what you do. if you have 7 natural numbers, then there must be at least one pair of natural numbers whose difference is divisible by 6, or there's another pair whose difference is divisible by 5, or there's another pair whose difference is divisible by 4, etc. Okay, so let's see the proof. The proof is you write bi for the ith number, so this is b, this is b1, b2, b3, etc., and you let ri be the remainder on dividing bi by k. There are 7 numbers here, and I'm going to divide by 6. So there's got to be 7 remainders, but there's only 6 possible remainders. You could have remainder 0, remainder 1, remainder 2, remainder 3, remainder 4, remainder 5. But you can't have remainder 6 or 7 or 8. If you're dividing by 6, you can't have remainder 6. You just can't. Okay, so there are 7 numbers. When you divide each of these numbers by 6, you get 7 remainders. And there's only 6 possible boxes. This is like 7 pigeons and 6 holes. Some hole gets 2 pigeons. So the remainders have k many possible values, 0 to k minus 1, but there are more than k many remainders, and so 2 of the remainders are equal. Well, if 2 numbers give the same remainder, then 1 minus the other is divisible by k. So you have this collection of numbers, and no matter what you do, you can't make the property disappear. So like I said, you say to yourself, okay, well, 3 minus 9 is negative 6. So I'll adjust the 3 to be a 5, and that way 5 minus 9 won't be divisible by 6. 12 minus 5, that's 7, so I'm still good. And so now you start going in and going in, and you adjust and adjust, and you just no way to figure it out. So this collection of numbers has to have a property. No matter how much you squirm and turn, it doesn't matter. The collection of numbers has to have the property that at least 2 of them are have a difference that's divisible by 6. 2 of them leave the same remainder on division by 6. Okay, another example, Ramsey's theorem. So the way it's often phrased, this is a small scale version of Ramsey's theorem, but it gives the idea. So you have 6 people at a party. So in your head, you have a mental picture of 6 people at a party. Either there are 3 of them that are mutual strangers. Mutual strangers means that each one is a stranger to the other 2. Or else there are 3 that are mutual friends. So it might be this one, and this one, but anyway, there's got to be either 3 that are mutual strangers or else 3 that are mutual friends. It cannot be the case that there are 2 that are that you miss one of those 2 cases. That can't happen. So how's it go? Obviously it involves the pigeonhole principle because it's in this section. So you imagine a graph. You draw the 6 people as nodes. You connect the nodes with a green, let's say edge if the people are friends, or a blue edge if they're strangers. Okay. So pick a node, doesn't matter, just pick a node. There are 5 edges. That is to say, for each person, there are 5 other people in this collection of partygoers. For each node, there are 5 incident edges. By the pigeonhole principle, at least 3 of the edges are all the same color. You can't have, if there's 5 edges, you can't have that the 2 of them are red, 2 of them are green, and the other one is indeterminate. That doesn't make any sense. So by the pigeonhole principle, at least 3 of the edges are all the same color. It might be 4, but at least 3 are all the same color. And suppose we'll name the nodes that they connect. So they connect N to P, N to Q, and N to R, just to give the nodes a name. Now think about the edge that connects P to Q. If the edge that connects P to Q is a color capital C, this color here, why then we have N, P, and Q are all mutual friends. They're all the same color, and so they're all either mutual friends or mutual strangers. And the same reasoning holds for N, Q, and R, and also for N, P, and R. Okay, so we can't have that 2 of these are connected by the same color that connects N to each of the 3. Okay. All right, so the only remaining case is that the edges connecting N, Q, and R are all the other color. So if C is green, then they're connected by a blue edge. But now the 3 of them are all mutual, so we're done. So you get the idea with the pigeonhole principle that you can get these reasoning, you can get these conclusions, but you're not sure. For example, here you're not sure which 3 it is. You know there's 3, but you don't necessarily know which 3 there is. Here's another example. So computer games use an awful lot of trigonometry, Instead of continually recalculating the values, if you want to calculate the tangent of an angle, for example, instead of continually recalculating the values, the graphic chips just use lookup tables because that's big O of 1. So here's part of a lookup table for tangent. So 0, the tangent is 0. 0.1 radians, the tangent is 0.1. But 1.00 radians, the tangent is 1.56, like that. But what graphics cards also need is the arctan, the angle whose tangent is y over x. Computer games need an awful lot of arctangents. So we could think to leverage the existence of this table by saying, instead of going left to right, instead of going from the angle to the tangent, for arctan we'll just go from the tangent to the angle. That's all. We'll just go right to left. However, you can see that this table has 100 rows, 101 rows, but it has 157 values. It needs to have 157 values to get the arctangent. There must be some values missing on this other side. We have 101 boxes, but we have 157 pigeons, so that's not working. So there must be some values that are missing on the other side. I don't know what they are. You could figure it out, but I don't know what they are. Well, so by the pigeonhole principle, there are tangent values that are not on the right-hand side. So our algorithm can't just look up the desired tangent on the right and return the associated radian number. Instead, it has to do something where it interpolates between the two or something like that. Okay, so the pigeonhole principle shows you that you can't, that if you have a tangent table, you can't get for free an arctangent table. One last example here. So data compression. Data compression is a function on a set of binary files. So you have files on a disk, binary files. I'm going to call that F. And data compression is a function that takes in a file and puts out a file. So, for example, when you zip a file. So it'll be the case that the well, I seem to have messed up the notation here. This is supposed to say the size of the file C of F is less than or equal to the size of the file F, but I've somehow messed up the size. Apologize about that. The size of the file C of F is less than or equal to the size of the file F. For at least some files, you need that C of F is strictly less than F. The size of C of F is strictly less than F. Data compression is called lossless if it allows the original data to be recovered from the compressed data. So we've all seen this kind of thing. So if I list, for example, the file that makes up these slides, pigeonhole.pdf, then it tells you that it's 312,000 bytes. But if I use the compressor gzip, then it shrinks to be 297,000 bytes. I made it smaller. Gzip likes to put a gz at the end so that the two files don't get confused. Okay, so I made the file smaller. This file, pigeonhole.pdf, got shrunk by gzip. But I want to prove that what we just did, in some sense, is impossible. Lossless data compression is impossible. You cannot shrink all files. You cannot shrink some files and leave other files the same size. Lossless data compression is impossible. All right, so obviously it's a pigeonhole principle. So you let S of L be the collection of all files of length at most L. Now we know that compression takes a file of length L and maps it to a file of length less than or equal to L. Suppose that the file F0 compresses to some smaller, strictly smaller size, like this file compresses to a strictly smaller size. So you take L to be the smaller size. Then the collection SL is the image of all the files in SL as well as the image of F0. So the pigeonhole principle, that's no good. You have sort of 101 pigeons to put in 100 boxes. So by the pigeonhole principle, at least one member of SL is the image of two files. That's not going to work. That's not lossless. If you go to decompress that file, you won't know which file to decompress to. So that contradicts that the compression is lossless. So basically what happens with data compression is that you shrink some files. Some files you shrink a lot, but a couple of files grow. So I want to make a point about the pigeonhole principle that might strike a person as interesting. A person who's in this class usually is here because you have kind of a computing mindset. You think about doing things by saying, well, we'll have a loop and then we'll flag the cases where this kind of stuff. In mathematics, a constructive proof is one that demonstrates the existence of some mathematical object by creating the object or by describing how to create it. A non-constructive proof, sometimes called a pure existence proof, demonstrates the existence of an object but doesn't provide a means for constructing it. So arguments using the pigeonhole principle are typically not constructive. We had 13 people. We wanted to say that 2 of them have the same birth month, but we don't know which 2. We only say we know there are 2, but we don't know which 2. So arguments using the pigeonhole principle are typically non-constructive, and so for a person with our kind of mental mindset can sometimes feel a little frustrating. You're like, okay, but which? Sometimes you can later go on to decide which it is once the pigeonhole principle gives you that there is one, but nonetheless a person can feel, well, wait, which two? Okay, anyway, so that's the pigeonhole principle. Very good. So stay well.